0 factorial is 1 factorial is 1, 2 factorial is 2. So far, everything feels completely normal, but now comes the paradox. What if the derivative of x factorial were equal to pi times x factorial? That sounds impossible, but factorial can be extended into a continuous function using the gamma function. Once we do that, we can divide its derivative by the function itself and graph the result. And something surprising happens. The curve hits y equals pi, which means the equation is actually true for some value of x. So now the real question is, where? The gamma function came first. It is defined by an integral, and unlike ordinary factorial, it works for real numbers, not just integers. That means factorial is not just a list of separate values. It is actually part of one smooth curve. When we graph gamma of x plus 1, something beautiful appears. At the integers, the curve lands exactly on the familiar values, 1, 1, 2, 6, 24. So x factorial is really gamma of x plus 1 in disguise. And once factorial becomes continuous, we can finally ask the question that seemed impossible before. What is the derivative of x factorial? We start with the equation we want to solve. The derivative of x factorial equals pi times x factorial. But factorial is not naturally a continuous function, so the first step is to rewrite it using the gamma function. Since x factorial equals gamma of x plus 1, the equation becomes gamma prime of x plus 1 equals pi times gamma of x plus 1. Now divide both sides by gamma of x plus 1. That gives gamma prime of x plus 1 over gamma of x plus 1 equals pi. And this ratio is important because it already has a name, the digamma function. By definition, psi of z equals gamma prime of z over gamma of z. So if we substitute z equals x plus 1, the whole problem collapses into one compact equation, psi of x plus 1 equals pi. We now know that our equation has become psi of x plus 1 equals pi. But that raises a deeper question. What exactly is psi? To answer that, we go back to the gamma function itself. Gamma of x plus 1 can be written as an integral from 0 to infinity of t to the x times e to the minus t d t. This is the raw material. Now we differentiate with respect to x. And here is the key surprise. When you differentiate t to the x, a logarithm appears. That is where the natural log enters the story. So psi is not just an abstract symbol. It comes directly from differentiating the logarithm of gamma. Next, we make a clever substitution that transforms the integral from 0 to infinity into 1 from 0 to 1. That reveals a hidden structure. Inside the new form, a geometric series pattern appears, and once that pattern is expanded, everything opens up into an infinite sum. In the end, psi of x plus 1 becomes a beautiful series made from simple fractions. So psi is not mysterious anymore, it is a series. And that series is what we will use next to uncover its deeper connection to the harmonic series. We have now reduced the original problem to solving psi of x plus 1 equals pi. For positive x, the series behaves nicely. Every term stays finite, the series converges, and the digamma function increases steadily. That means, on the positive side, we should expect at most one solution. Now let's visualize it. This yellow curve is psi of x plus 1, and the dashed horizontal line is y equals pi. As x increases, the curve rises slowly but continuously. So the strategy is simple. Test a few values and trap the crossing point. At x equals 10, psi of 11 is about 2.4, still below pi. At x equals 20, it is about 3.05, still below pi. But at x equals 25, it is about 3.2, which is now above pi. So somewhere between 20 and 25, the curve must cross pi. And when we zoom in numerically, the positive solution appears. X is approximately 22.6. On the negative side, everything changes. The digamma function develops poles at the negative integers, where psi of x plus 1 blows up to infinity. These poles break the graph into separate branches, and on each branch the function sweeps from negative infinity to positive infinity, which means it must cross y equals pi once on every branch. So the real shock is this. The equation has not just one solution, but infinitely many real solutions. The first few are about -1.238, -2.283, and -3.312. So this strange factorial equation is not a one-time coincidence. It happens again and again forever. Now we can see the full picture of the derivative equation. The derivative of x factorial equals pi times x factorial. The digamma function crosses y equals pi once on every negative branch, and once more on the positive side. So this surprising equation has infinitely many real solutions, including one positive root near 22.6. What seemed impossible at first is actually true. Thanks for watching.